Okay, so let's start differential equations. So this is the first chapter in Ross's book. It starts like this. In the first section we have classification of differential equations, their origin and application. And today we are going to see the classification part. So in the beginning of the chapter, the author raises some questions, and the questions are these. What are differential equations and what do they signify? Where and how do differential equations originate and what are their uses? And if you are given a differential equation, what do you do with it and how do you do it? So these questions are going to be answered throughout our study at different stages, and the answers will become more and more clear as we continue our study. The author has identified three major aspects of the study of differential equations, and they are theory, application, and method. Well, actually theory, method and application, because in that order it goes, but I wrote application first. Okay. So we will see the theory aspect, we will also see the method aspect where we will develop methods for solving specific types of differential equations, and then we will also see their application. Okay, so let's start. The first thing, of course, is the definition of a differential equation. That should first of all be clear. Let's first see the formal definition and then we will try to understand its meaning. A differential equation is an equation involving derivatives of one or more dependent variables with respect to one or more independent variables. Okay, so that is basically the definition of a differential equation. It's an equation which involves some objects. The objects are derivatives. Derivatives of what? Of course, we differentiate a dependent variable with respect to an independent variable. Now, the number of dependent variables may be one or may be more than one. The number of independent variables also may be one or may be more than one. Any such equation is called a differential equation, but there is a caveat, there is a condition. Let's look at these two things. You already know this formula from calculus. Where a is some constant, some real number, and x is a real variable. You know this fact. Okay. This is also a derivative. So should we call this a differential equation? No. But why? That is one question. Another thing is this. Suppose u and v are two differentiable functions of the independent variable x. Then again we know from calculus that their product is differentiable and the derivative of the product is given by the product formula. U times dv dx plus v times du dx. Is this a differential equation? It also involves derivatives. It also involves dependent variable, independent variable. If you give this e to the power ax a name, say y, then y becomes a dependent variable. It depends on the independent variable x. Should we call these things differential equations? No. The thing is that these are not equations, these are identities. The difference between an identity and an equation can be understood simply by considering this thing. Suppose that x and y are real numbers. Okay. You know this fact from the system of real numbers. Addition of real numbers is commutative. Now this equation, this equality is true. I should not perhaps say equation. This equality is true for all real numbers x and y. Such an equality we call identity, which is true for all elements in a given class of objects on which the relation is given, on which the equality is given. If it is true for all elements in that class, then it is an identity on the class. Similarly, we have sin square x plus cos square x equal to 1, where x is a real variable. This equality is also true for all real numbers x, as opposed to these things. So this is also an identity. This is also an identity. These are not equations. As opposed to that, say someone writes sin x equal to 1 divided by 2. This is also an equality which involves a real variable x. Now, however, this is not true for all real numbers x. So on the class or on the set of real numbers in which this equality has got a meaning, there are some specific values of x for which only this is true, not for all x. So this is an equation. These are not equations. This is an equation which has to be solved to find those values of x for which this is true. You can think of these also in that sense that here, say we can think of finding x, but we already know that these are true for all x and y, the first one, and for all x, the second one. So the question of finding x or finding x and y here are trivial. That question is trivial. That's not exactly trivial in this case. That's why we call this equation. And these are identities, and that's why, you know, if you recall, this is called a trigonometric identity, whereas this is a trigonometric equation. Similarly, these are identities on the class of all differentiable functions of a real variable. You take any two functions u and v, this is true. This second identity, it's somewhat like this one. This is also true no matter what real number a you take, and in this case something else is also it can be seen. You see here in these equations, I mean in these identities here and here, x and y really were variables. Here, however, well, you have x, but the objects here are not, the objects of interest in a differential equation are not variables but functions. The function that we want to find out from the equation should be unknown. If we already know it, then there is nothing to do. Here there is no unknown function. We know precisely what the function is that we are differentiating. It's an exponential function. Here, however, the functions are unknown u and v, but the identity is true for all differentiable u and v. So that's why this is an identity and this is just a relation. So these are not equations. In order for an equality like this to be a differential equation, it should have an unknown function. It's going to link dependent variables and independent variables through their derivatives, right? We should not immediately know or know beforehand what that function is that links dependent variables and independent variables. We have to find those functions or that function by solving the differential equation. If no such unknown function is there, then the relation is not a differential equation in spite of having derivative. And even when you have unknown function, it should not be an identity like this. It should be an equation like this. Okay, so that these are differential equations. All right. The definition we have just seen now is quite general. It allows for such an equation to have any finite number of dependent variables and also any finite number of independent variables. So let us now see some examples that will make these things more clear. Example 1. Consider the following equations. The first equation is this: d squared by dx squared plus xy times dy dx whole squared is equal to 0. So we give this number also. We are going to talk about these equations, discussing some matters. Then we will refer to them using these numbers. Let's consider this next one. D to the power 4 x dt4 plus 5 d squared x dt squared plus 3x equal to sin t. So this is 1.2. Two more, del v del s plus del v del t is equal to v. This is 1.3. And finally, another one. Del squared u del x squared plus del squared u del y squared plus del squared u del z squared equal to 0. So this is 1.4. Okay. So from these equations you can clearly see that there are several types of things that one can see. One can see that there are derivatives of somewhat large order, not just first derivative dy dx. Here we see fourth derivative. Here the dependent variable is y, the independent variable is x. You can clearly see, just now we said that it should not be immediately clear which function links x and y. In other words, y is which function of x. That's not immediately clear. It will be clear only after solving the differential equation, that the function will come out or a class of functions comes out. So you see here we have first derivative, but we also have second derivative. Here the dependent variable is x, the independent one is t. Here fourth derivative is available, but also we have sin t, sin function of the independent variable is on that side. In this one we do not have ordinary derivative but partial derivatives. Here the dependent variable is v, and presence of partial derivatives indicates that v is a function of two independent variables s and t. On that side also we have v, but here the partial derivatives are first order partial derivatives. In this one we have second order partial derivatives. The unknown function is u, so we are saying the function is u. Sometimes we do not distinguish between the dependent variable name and function name. You already know this thing from calculus. So u is the unknown function or the dependent variable, and this time u depends on three independent variables x, y and z. So because of many things happening, it becomes clear that we need some kind of classification so that we can neatly classify some types of differential equations, and then we can study each time. We can try to formulate ways of solving each time or say something qualitative about each time. So that's the next thing. We want to somehow classify these differential equations. The first classification, which is quite clear, is whether the equation has one independent variable. In this case the independent variable is x, here the independent variable is t. In each case only one independent variable or more than one. Here there are two independent variables s and t, here there are three, and accordingly you get ordinary differential equations and partial differential equations. That's the first classification. So let's see the definition though. If a differential equation, we cannot write differential equation again and again, so let me just write DE. Okay, if a differential equation involves only one independent variable or more accurately, I should have written if a differential equation involves derivatives of one or more dependent variable. Okay, let me just write like that. Yeah, why am I diluting the definition? If a differential equation involves derivatives of one or more dependent variables. See, the number of dependent variables can be more than one. That's not our concern. In other words, the number of functions which are unknown, that can be more than one. but here the classification is based on the number of independent variables, the variables which come below. Dependent variables, but only one independent variable is called an ordinary differential equation. If, on the other hand, okay, we are going to need this. Let me not just erase these things now itself. If the equation involves partial derivatives of one or more dependent variables with respect to WRT more than one. I am running out of space. Okay, we will again write the equations, okay, as we need them again. We will write them again. More than one independent variable then it's called a partial differential equation. So let me again write the equations. D squared y dx squared plus xy times dy dx whole square equal to 0. So this was 1 1. Then the fourth derivative of x with respect to 2 plus 5 times the second derivative plus 3x equal to sine t, and the other one was del v del s plus del v del t is equal to v. So you can clearly see that 1 1 and 1 2 are ordinary, whereas 1 3 and 1 4 are partial differential equations. 1 1 has only one independent variable, which is x, and so does 1 2, where the independent variable is t. 1 3 has two independent variables, s and t, and 1 4 has three independent variables, x, y and z. Okay, so that's the first classification. In fact, that's just example 1 2. I mean, we saw example 1, which is example 1.1 actually. In example 1.2, we just note that these two are ordinary and these two are partial. All right, so after seeing these things, there are further ways of doing classification. Both ordinary as well as partial differential equations are next classified according to their order. the order of the highest derivative in a differential equation is called the order of the differential equation. The order of the highest derivative present in the equation is called the order of the differential equation. And that derivative, these derivatives may be ordinary or partial depending on what type of equation we have. In the first one, in 1.1, the highest derivative is the second derivative of y with respect to x. That's why its order is 2. In this one, the highest derivative is the fourth derivative of the dependent variable with respect to the independent variable. So this one is a fourth order differential equation. Here, the highest partial derivative, the order of the partial derivative is 1. So it's a first order partial differential equation. Here, the highest order of the any partial derivative is 2. Actually, all the derivatives you see here have order 2. They are all second partial derivatives. So this is the second order partial differential equation. And then we also have the notion of a linear equation, which at this stage has been defined only for ordinary differential equations. Okay, we will see afterwards what linear partial differential equations are, but right now we are only going to see what type of equation that is an ordinary differential equation will be called linear. That's the next thing. Linear equations, linear differential equations are easier to solve than the non-linear ones. That is why we need this classification. Just like linear ordinary equations are easier to solve than non-linear ones, somewhat like that. We should state clearly an ordinary differential equation. An ordinary differential equation of order n is called linear. We need to hold on. We need to also say what the variables are. Although you can simply write y and x, but still an ordinary differential equation of order n with dependent variable y and independent variable x is called linear if it is or can be expressed if it either already is or can be expressed in the following form. This is the form. a function of the independent variable x times the nth derivative of the dependent variable with respect to the independent variable, plus again a function which may or may not be this one, something different, times the previous lower derivative n minus 1. In that pattern, the sum goes a n minus 1 of x, again a function of x, times the first derivative plus a n of x times y equal to again some function of the independent variable x. If our differential equation is either already in this form or it is in some other form which is equivalent to this form. Equivalent means if you can manipulate the equation without losing anything or without adding anything from outside and get this. You can turn, essentially you can turn the given equation into this form without losing anything or gaining anything, then it is called a linear equation. Its nth order we need to mention for the order to be n, where a naught of x is not identically 0. The function a naught of x, of course, it should not be identically 0. This is similar to how you write a polynomial equation of degree n. You mention that the coefficient of the highest degree term is a non-zero real number. Here in place of number you have function, so it should be a non-zero function. It should not be the function which is identically 0 everywhere. So this is how a general ordinary differential equation of order n looks if it is linear. Now there are some observations about this form. The first observation is this: the dependent variable y and its derivatives and its derivatives of all the orders present occur to the first degree only. In other words, you see these derivatives. Well, although this is not identically 0, some of the other functions may be 0 identically. So those derivatives may actually be absent, but still we can consider them. The thing is that those coefficient functions ai of x which are not identically 0, for them the derivative appears only to the first degree. You do not see square or cube or anything else of these derivatives. Also, the dependent variable or unknown function y simply appears as y. No y square, no y cube, nothing like that. That's the first observation. The second observation is that no products of these terms. Okay. That means not only do we not have higher powers of these quantities in the equation, we also do not have products of these quantities. For example, here you do not see y times dy dx or some derivative times some other derivative, or maybe a product of say 3 or 4 of them, one of them is y. That such things, such cross term products also are not present. Whenever a derivative is appearing, it is appearing to the first degree and also no such products. That's the second observation. And the third observation is that no transcendental functions of these quantities are present in the equation. Let me keep the equation and continue from here. Okay. What is a transcendental function? To know what a transcendental function is, we need to first of all know what is not a transcendental function. Such functions are called algebraic functions. Because we are interested only in a function of, the type of function we are interested in has only one independent variable. It's a function of a single real variable. So this is the definition of an algebraic function. Suppose you have a function y equal to f of x. Okay, y is your dependent, x is independent. Say there exists a polynomial p of two variables u and v, and it has integer coefficients. In other words, if you bring in the language of ring theory, it's easier to write what we mean by that. P of u comma v is an element of this polynomial ring. It's a polynomial ring where there are two indeterminates u and v and the coefficients are integers. A typical element of this ring is something like this, say 2u square plus 3u plus 4uv plus v to the power 5. In simple language, it's a polynomial, but there are two unknowns, u and v, and the coefficients are integers. Suppose something like that is there, such that if you substitute in this, not in this expression, but in this polynomial, if in place of u, you substitute x, and in place of v, you substitute f of x. Say you do this, then it becomes identically 0. It becomes the 0 polynomial. You make these substitutions and you do your calculation according to how you manipulate polynomials, and whatever ultimately you end up with, that has all coefficients 0. That's what we mean by the polynomial being identically 0. If this happens, if there exists such a p for which this happens, then f is called an algebraic function. Examples of algebraic functions are the functions that you see all the time. For example, polynomial functions themselves are algebraic, rational functions are algebraic. In fact, any algebraic function can be obtained by starting with the identity function x and constant functions and applying a finite sequence of plus, minus, product, multiplication and taking nth root. So, by applying any such sequence, whatever we ultimately get, those are algebraic functions. And functions which are not algebraic are called transcendental functions. Examples of transcendental functions are the exponential function, the natural logarithmic function. Okay, so these are examples of transcendental function, sine function. So what the third observation is that in our equation, not only do we not have higher powers of y and their derivatives or products of them, but no transcendental function of these things. For example, if your equation has say sine of dy dx, then that's not a linear equation. Or say e to the power dy dx, no, then it's not linear. Natural logarithm of dy dx, or say the nth derivative, or sine of dn y by dn y dx n. So if those things are present, then that's not linear, but those things are not present here. Well, you can say that what's the need for saying this? They are anyway not, we can see that they are not present, but do not forget, any equation which either is in this form or can be transformed in this form. So after you try to transform it from its original form, which may have such functions, say sine y is in fact present there, but after you do something, there is no longer any sine y. Okay, if ultimately after doing some calculations, some manipulation, the original equation can be turned into this form, then it is linear. And these observations also indicate that if these things were present here, then it would not have been linear. And again, keep in mind that this is linearity has so far been defined only for ordinary differential equations. Okay. So let us now see some examples of linear and equations which are not linear. This is actually example 5. Examples 3 and 4 involve those things that I did not really write systematically, where we saw ordinary and partial differential equations, those things, okay, order those things. So here we come across new equations. D squared y dx squared plus 5 dy dx plus 6y equal to 0. Say we call it 1, 5. Then the fourth derivative plus x squared times the third derivative plus x cubed times the first derivative. The second is not there, or is there but the coefficient is 0. This is equal to x times e to the power x. Say this is 6. both of these equations are linear. Why? Because they already are in that given form, in the form that you saw in the definition. Here, this is a second order linear ordinary differential equation. Second order because this is the highest order term derivative, and the unknown function y, its first derivative and its second derivative all occur to the first degree. Also, we do not see any product of them, and also no transcendental function of them can be seen here. Similarly, this one is also linear. Here the highest derivative is the fourth derivative, then third, first, and then we actually do not see the y term present here, but that's possible. I mean, y is there but with 0 coefficient, and the right hand side is also not 0. Now something you can observe here which is somewhat interesting is that right now we said that no transcendental function of these things. We do have a transcendental function e to the power x of the independent variable, not of the dependent variable y or its derivatives. We do not see e to the power y or e to the power fourth derivative. Those things are not present. Okay, so here anything can happen with the independent variable, but the dependent variable and its derivatives should not get involved in such things. And that is why, in spite of it having exponential function, still it is linear. Okay, you see that. Next, the next definition of course depends on the previous one. And ordinary differential equation which is not linear is called non-linear. Alright, let us now see some examples of nonlinear equations. Nonlinear equations are much more difficult to solve than linear equations. I keep saying solve, although we haven't really talked anything about solving differential equation solution. Those things will come, okay. But I am just simply saying things ahead of time. D squared by dx squared plus 5 dy dx plus 6y squared equal to 0. Say this is 7. Next, d squared by dx squared plus 5 times dy dx cube plus 6y equal to 0. Say this is 8, and another one plus 5y dy dx plus 6y equal to 0. All of these three equations are non-linear. Here the derivatives are to the first degree but not y. Y square has appeared. That's the reason for this equation to be non-linear. Here the third power of the first derivative has appeared, cube of dy dx. That is why this is non-linear. Here product of y and its first derivative has appeared. That's why this is non-linear. Okay, so now the notion of linearity and non-linearity has become clear. And finally, ordinary differential equations which are linear can further be classified into two types. Linear ordinary differential equations can further be classified into two types depending on the type of coefficients the terms have. In this equation, these coefficients 1, 5, 6, these are also functions of x, of the independent variable, but all of them are constant functions. So that's why it's called a linear ODE, ordinary differential equation with constant coefficients. Here, however, although this is 1, but here we have a non-constant function of the independent variable, x square, x cube. So this is an ordinary differential equation that is linear but with variable coefficients, not constant coefficients. And we will see later that there are different ways of solving these two types of equations. And after this also we are going to see some other things. For example, if the right hand side is 0, the equation is called homogeneous. If not, it's non-homogeneous. So all those things are going to be considered. So this is how a preliminary classification of differential equations has been achieved. Mainly we have just done this. After classifying all differential equations into ordinary and partial, we then solely concentrated on ordinary differential equations. We did not really see partial differential equations or their further classification, nothing about that. But we are going to see, okay, eventually we are going to see. So let me just end the video here itself. So this is our classification part. After this, we are going to see where and how differential equations originate and how they are used and why are they needed. So these things we are going to discuss next. Tomorrow also there is an upload, but it doesn't have any pattern. So I am just going to search something and show you. It's not related to anything. You know how it goes. Okay. So see you tomorrow with that. Until then, this is me, Lucifer from A Mathematical Room. Have a nice day.